Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 126. It's on the wave-particle duality of light. There's an old story of 4 blind men and an elephant, and they're each touching it at different points. And so this guy says it's pointy, this one says it's strong and sturdy like a tree, this one says it's flat like a wall, and this one says it's a snake. Now they're all right. They're all just touching different parts of the elephant, and light is like that. Depending on our scale, it can be both a wave and a particle. And so light travels as photons, and those photons can act as waves and particles. Evidence that showed us they're waves is their interference. They can interfere with one another, sometimes build up the waves, sometimes build them down.
Slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit another, sometimes build up the waves, sometimes build them down. And they also, if we look at them as a particle, the photoelectric effect tells us that photons are quantized. They travel in these discrete units like particles. And so if you're a physics student or a physicist, how do you know which model to use? Well, it really depends on a sense of scale. And so we would use a wave model if the size of the objects that we're measuring are comparable to the wavelength of the light. And we would use the particle model if the energy that we're studying is comparable to the energy of a photon. Remember, which is described as Planck's constant times the frequency of the photon itself. Let me give you a little bit of history. The first person to tackle this issue was Isaac Newton, and he thought that it traveled in these small microscopic corpuscles, or these small particles. And then finally Thomas Young looked at that evidence, gathered more evidence, and said that they're waves. And so scientists looked at this for hundreds of years. And so if we kind of look at all of the evidence and kind of go through those 2 particle and wave model, we could first start with reflection. Do they bounce off objects? And we would say yes and yes. If we look at refraction, can they bend as they move from one medium to another? We would say yes and yes. If we look at interference, can they interfere with one another? The particle model doesn't hold up. They can't interfere with one another, but the wave does. Do they diffract? Do they bend around objects, or as you go through an opening? We'd say particle no. We would say wave yes. What about can they be polarized? In other words, when they're traveling in one dimension, can we use small slits to just limit the amount who go through? Say no, and we'd say yes for waves. So waves are looking great. And finally, the photoelectric effect came around, and Einstein came around. And what it showed is that the wave model doesn't work. Only the particle model works. And so now we've got a duality, this view of light as both a wave and a particle. And so what's the answer? Well, both are right. And so how do we know which model to use? Again, it's a sense of scale. And so if we're looking at objects that are comparable to the wavelength of the light, then we use the wave model. But if we're looking at experiments where the energy is comparable to the energy of a photon, it's going to be a really small amount of energy, then we have to treat them as a particle. And so did you learn to select a model that's going to be appropriate for measuring photons? It all comes down to the size of the wavelength, the size of the energy, and I hope that was helpful.